I have heard that there are multiple big issues right now in blockchain, and these issues are interoperability, scalability, and another one is security. So I'm going to focus on security. As you may have heard, probably the most prominent attack was the DAO hack, where the attacker drained Ether from a smart contract. So that happened 2 years ago. Now, a few months ago, there was another attack, which was named Batch Overflow. So nobody lost any money through this attack, but the attacker was able to mint a lot of coins. And consequently, the exchanges stopped deposits, and people couldn't really use ERC tokens for trading at these exchanges. So, for example, we as Quanstamp were asked by Binance to audit all of the ERC20 tokens that were trading on their exchange. And there are multiple aspects of security of smart contracts. So there may be issues with the language itself, like Solidity or the way you use it, issues with EVM, or basically issues with properties of blockchain itself. So, what do people do right now? Typically, developers write tests, but as we can see through these attacks, the tests are not good enough. Fortunately, there has been decades of research in computer-aided verification methods, and these methods basically they do exhaustive search of your code, and then you can get much better assurance that the code will do what you want to do, and it will be safe before you actually deploy it. And in this presentation, I'd like to talk about two methods and explain how they work on examples. So these methods, they've been used by big companies, although traditionally they were used typically in mission-critical systems because they were expensive to apply, and they required a lot of expertise and a lot of training. Now, I think that smart contracts, they're important enough and small enough right now to apply these methods and make the contract secure. So I've got two snippets of source code. It's nothing advanced. Basically, the snippet on the left withdraws balance, and the snippet on the right transfers balance from one account to another account. So the first method is symbolic execution. Basically, what it does, it executes the code on symbolic inputs. And by symbolic, we mean that it is a set of inputs that satisfy certain criteria. So each box in the slide represents a symbolic state. And these arrows basically take you from one state to another one. And there are certain conditions that get you from state to state. Now, if you concatenate all of these conditions, some of the states won't be reachable, and these are marked on red. Now, some other states will be reachable, and they will satisfy certain property, and some will not. So, for example, we can think about these properties as division by zero or reentrancy. Come on. Yeah, so here is the transfer balance snippet. We've got three conditions, alpha, beta, and gamma. Basically, the first one checks whether the sender's balance is more than zero. Then it checks whether the sender is a member and whether the dest is a member. And if these conditions are satisfied, then the balance is updated. Now, if you execute it symbolically and alpha is not true, then you go to the last line and there is nothing to check, everything is fine. And then the same happens with beta and gamma. Now, if all of them are satisfied, you get to the if statement and check whether there is any division by zero or reentrancy. Fortunately, in this piece of code, there are no issues. The reachability is computed by SAT or SMT solvers because there are multiple Boolean combinations, and basically you want to generate the formulas that will get you to the state that you would like to check. So now let's look at the second example. So here we've got the if statement, and let's say we get into the if statement, and you can see that there is this value transfer, but it really means that any contract, who is the sender will be called to receive that value, and after that the balance is updated. But if you get into line 4, you can either proceed to line 5 and 6, which is OK, or you can proceed to line number 4, then get to another contract, and that other contract will call your function withdraw again. And what will happen then, you can drain the balance, and this is exactly what happened in the DEO attack, where the attacker basically used his own or their smart contract to withdraw the balance by overwriting the fallback function. So the second technique is model checking. It is a bit different in the sense that it is not a push button technique. So basically you construct a model of your code, and then you have a specification with properties that you would like to check. So let's look at this snippet on the right. It transfers balance, and the invariant that must be satisfied is that bank's balance stays always the same. I know there is not much time, but can anybody spot any problem with this invariant in this piece of code? All right, so here is the thing. If I transfer the balance to somebody else, everything is OK. But imagine if I transfer it to myself. As I set the balance in line 14 to 0, effectively, I'll be erasing coins or tokens from this contract. So clearly, the invariant is not satisfied. So model checking is one of the techniques that could detect this violation. So these techniques are great. However, there are problems with scalability. For example, you may have a lot of states, so it may take too much time or too much memory, too many resources to explore all the states. Or maybe the state itself may be huge because you have lots of variables. Or computer reachability may be a very, may take a long time because this is an NP-complete problem itself. So this is a short comparison of these two techniques. So let's say both of them are exhaustive, though they may be bounded. So you may have some restrictions on the number of loops that you consider. Model checking can handle concurrency, but symbolic execution cannot. And finally, symbolic execution basically checks your contract for a pre-specified set of properties. So for example, like division by 0 or reentrancy. But basically, you just put your contract into it, and you get some report. And then you probably need to remove the false positives. Model checking technique, on the other hand, takes the code or your model and the specification. The problem is that writing this specification is a difficult task, and typically requires expertise. But it is more generic in the sense that you can specify yourself the properties you'd like to verify. So this is my last slide. Just wanted to say that we at Quanstamp, we are building a protocol and tools for providing better experience for developers when it comes to analyzing security of smart contracts. So we have a web application, and we also have a protocol, and we hope to secure smart contracts first for Ethereum, then other blockchains. Thank you.